Thank you very much. So my name is Nico Mansfeld and I'm with the German Aerospace Center. Today I'd like to present you some work on safety in human-robot interaction and in particular the concept of a so-called safety map. And this work I've been doing together with colleagues from Leibniz University of Hanover, and two of them are now with Technical University of Munich. So safety is a very important topic in nowadays human-robot interaction because we have all of these lightweight robots and physical contact is part of the process, so we need to ensure that a human is not harmed by any means. And in order to understand what safety really means, we need to do a proper injury analysis. So we need to do collision experiments. We also have to come up with collision models, and in order to get a thorough understanding of what safety means. And so many collision experiments have been done over the years. Okay, so now for doing safe human-robot interaction, we have basically three problems, namely control, planning, and design. In control, we are concerned about generating locally safe velocities. In planning, we want to generate safe trajectories, and in design, we want to generate, to design safe robot manipulators. Now, with these three problems, they also come with different perspectives. So control can be considered from a rather local perspective, while planning and design have to be treated from a global perspective. And we can make one analogy at this point. So if you consider a weather forecast, then you can determine the weather at one particular location, but you can also collect the measurements from various locations in order to generate the entire map. Okay, so for control and planning, many safety metrics have been proposed over the years, and they relate the current kinematic and dynamic surface properties to a certain metric that shall be as small as possible or below a certain threshold. And these safety metrics, they typically use collision models, so often very basic collision models, or sometimes even more sophisticated collision models, and there are many examples for these safety metrics, but typically the real injury data is missing. So, and what we want to do, so we want to base everything, so control, planning, and so on, always on a biomechanics fundament. So the main research question that guides our research since many years is, can we find a unified biomechanics way to tackle all of the three problems? So what we want to do is we want to use all available biomechanics data. We want a hierarchical tool stack that can be applied to any type of robot, and it shall be compatible with standards. Okay, and so our solution for control was proposed some years ago, and we came up with a so-called safe motion unit that takes as input the current robot reflected inertia, which can be seen as the mass that you perceive during a contact. Then we have the velocity and the curvature. And this information is mapped to a biomechanically safe velocity. And for this, we take this real injury data into account, and we use so-called safety curves where we relate the current robot reflected mass to a biomechanically safe velocity. Now, so we solved the control part, so the global point of view, and now we want to get this global perspective. And so here again, we have this local perspective, the control layer, and now we're interested in the global perspective. And so what we do first is we do a dynamic workspace analysis. So we take the entire motion range and the overall inertial and surface parameters of a robot. And from the injury data, we take the safety curves and also safety surfaces, which I will explain later, and combine these in a so-called safety map. And before going on into more details, I will comment a bit on our contribution. So first, so we do this global workspace analysis, and we also show how injury data can be processed to overall safety curves and safety surfaces, and we propose the safety map. Okay, so how does the safety map look like? So first we have the plane, which is spanned by the robot reflected mass and velocity. And now we want to relate entire robot designs to available human injury data. And here we have two examples of two robots, and so the Franca, Emika, and a DLR lightweight arm. And in the safety map, we can have the overall representation of the robots in terms of a mass velocity range or a task-specific subset. And of course, we also need the human injury data, so we have a human injury database, and from this database, we can generate these mass velocity representations. Okay, and in this database, the injury data, it may originate from various sources. It may originate from biomechanics, from forensics, from simulations. We may consider different body parts, injury criteria, and collision cases to sum up, in principle, all available data. And now, this safety map provides us with a very intuitive and visual way of doing safety analysis. So if you consider head injury, which is the red area here in this plot, you can see that both robots may produce this kind of injury because we have these intersections. However, hand and arm injury here can only be produced by the second robot. Okay, so this is the framework. This is what our goal, what we want to achieve. And now how do we process the robot and human data towards this representation? So I will start with the human data first. And so we start from a very basic collision model where we assume that any collision can be modeled in terms of a certain reflected mass, velocity, and curvature. Then we also may have different collision scenarios. So the human may be unconstrained, constrained, or partially constrained. Then at the contact point, you always have a certain geometry. And typically, you can decompose them into a set of primitive geometries like spheres, corners, edges. And in biomechanics, many different test setups have been used over the years. So drop test experiments, pendulum setups, and we classified all of them and came up with 4 principal test setups. Okay, and so using this classification now we collected a lot of biomechanics data from over 50 years of biomechanics research, and we summarized all of them according to this classification, and we stored all the data in a database. And from this database, again, we can generate these mass velocity representations that we need for the safety map. So now we found the mass velocity representations of human data. So how about the robot? So for every robot, the robot designer does a workspace analysis, right? And so for the entire robot workspace, now we want to find the maximum velocity and the reflected mass. So, and this is how we proceed. So we start with a simple robot that has a position T and orientation R. Then we sample the entire workspace with a uniform position grid, which is denoted capital T. Then the robot may have different orientations, and we also discretize the set of SO3 end effector orientations. Then the robot may be redundant, of course, and so we can sample a certain amount of node space configurations. And then the robot can, of course, move in every Cartesian direction, so we also have to discretize the principal Cartesian motion spaces. And so now for every position, orientation, node space configuration, and Cartesian direction, we determine the instantaneous reflected mass in a certain unit direction and also the maximum velocity. And this maximum velocity is determined by formulating a very simple static optimization problem, where we assume that the motor has certain maximum velocities and we move in a certain Cartesian direction and just want to maximize it. Okay, so of course, when considering verifying grids and all of these parameters, the computations can get quite complex. And however, everybody can tailor these calculations to its needs. So we can only select only a small workspace where the application shall be performed. We can select different motion spaces, and we can also adjust the granularity. Now, let's move on to some results. So now I will present the results for 2 robots, namely the Puma 560 and a lightweight arm. So this is how the results look like. So we sampled the entire workspace, we discretized, the workspace of the robots, and for every point and for 3 directions here, we determine the overall reflected mass and the reflected mass and velocity, and also the values for an exemplary cube where the dexterity is very high. And we do this in order to provide some typical values of mass and velocity. Okay, so let's consider a pick and place task now. So we want to combine, or we want to compare both robots for a standard pick and place task, and the robots shall be compared to each other, and we also compare them to the injury data that we collected. So this is the mass velocity representation of the Puma. This is the representation of the lightweight arm, and here we can see directly that the lightweight arm has typically lower reflected masses and lower velocities. This is real biomechanics data on head and chest injury. This is rather severe injury. And we also want everything to be compatible with the current norms. So these are the thresholds from the current standard ISO TS 15066. And in addition to the robot and injury data, we always have some performance requirements, right? And here we specify them in terms of a certain velocity band. So here the velocity shall be between 0.3 and 1.0 meter per second. So now we have all this information in one picture, in one map. And now the application designer, for example, you can determine, can I meet both safety and performance at the same time? Can I meet the current safety standards, and which geometries are critical? The robot designer, you can compare different robots, can compare the overall mass velocity range. You can compare performance requirements with safety, and so on. And in this work, we provided the framework, we proposed this, and our current research regards the integration of this framework into automatic safety evaluation, possibly also automatic robot design, and we haven't considered the influence of the payload yet. So if you add a certain payload, then the mass properties change and also the geometry. And ideally, we want to determine the influence on the safety map with only very little computational effort. To sum up, we proposed the concept of a safety map, which is a unified representation of robot collision behavior and human injury properties, and it allows us to do a very global and model-independent safety evaluation, and it is compatible with the current standards, and we believe it is a very powerful tool for practitioners, robot designers, and researchers. Thank you.
Are there any questions from the audience?
Very interesting work. One question, you've modeled the robot behavior. What about cause and effect? So the actual situation awareness behavior of the human, and trying to model and get that on the same map. Have you considered that, or has that been part of future work?
You mean that the human is aware of how the robot behaves or how the robot moves?
No, what I mean is the actual situation awareness of the human to the robot itself being a possible cause for any possible injury. So having awareness, or having, I guess, to model that situation awareness behavior. So you've got the behavior of the robot. I see that there's an opportunity for modeling the behavior of the human in various situations. Now, of course, harder to do, but I'm just wondering if you've considered that.
Yeah. Well, basically, we don't want the human to be aware of what safety means, but we want the robot to be aware of safety. So we want to integrate all this this knowledge of injury biomechanics and safe control into the robot, such that we can always generate safe motions, no matter. So even if there are entirely unforeseen collisions and unexpected collisions, which can always happen, right? And so we believe that we should, rather make the robot aware instead of the human.